Hello. So this is a pre-recorded talk for Data Umbrella. Like essentially, I gave this talk sometime in November, and there were some network issues, and so yeah, I'm just recording it again. And I think it would be useful if you're somebody who will be attending the rest of the events or webinars that will be happening with PyMC for Data Umbrella. They're mainly there to get you accustomed to, contributing to open source and probabilistic programming. So this first talk, it's about array operations in Python. Like the aim of this talk, I think, is for people who, are familiar with an object-oriented programming language, like one of them at least, and so they can get some takeaways from this talk and probably the other events that will be happening. Then those will be more useful for you if you're someone who didn't use Python very frequently. So just like a quick brush up. This is by no means a Python tutorial because thousands exist and I cannot do that in 45 to 50 minutes. So yep, let's get started. So yes, this is Meenal. That's me. My pronouns are she and her, and whatever you would prefer. I'm currently studying computer science and mathematics at University of Delhi. And this summer, I was a Google Summer of Code student at PyMC, and now I'm continuing helping around with the amazing team over there. And you can contact me over here. My email and website are given. So yeah, this banner is basically generated from, like, I just wanted to mention it in the talk. It's generated from this code that I've linked to. This entire slide thing is available on the website, so you can go check it out. And so there's someone called Colin in our team at PyMC, and so he's really cool. I mean, great at data visualization stuff. And so yeah, like most of the code for this is taken from him, and then it's like I modified a little and tinkered with it, and now it's pretty cool. So yes, let's get started. So we'll basically be doing like, I introduced the whole series and myself and everything, and then we'll be doing basics of Python, like data types and list comprehension, and then a little of NumPy. Like NumPy is like probably the most relevant part because that's something that we use in PyMC or more or less any other scientific open source software in Python, which is what our target is. So Python is basically like, it's pretty easy. It is like relatively, at least for me, when I learned C or something, the syntax is like very readable. Like obviously it's not as fast, but there's there are things like dynamically typed, and I mean that's something that's very controversial, so I won't go there whether you should have statically typed languages. But yeah, it's useful for quick prototyping. Like you just, like, whenever I think of something and I just open up a notebook and just type in 3-4 lines and I can just test out some idea in my head. So it's useful for that. And one of the things that has been happening is like the machine learning hype, but except that as well, there are like a large number of like scientific softwares that are there on Python, like PyMC being one of them, which we hope you might contribute to after viewing all of these. And so yeah, there's this GitHub repository, PyMC -data -umbrella. And I mean, if you want to go along and try out everything, you can have an installation of Python and a terminal on which you can do all of this. But we did this thing where you can go to the website and all these cells are executable. There's a link for everything that's happening in this session, and you can execute the cells as you go, so you don't even need an installation. But I think if you really want to learn Python, you should probably install it. But yeah. So yeah, I mean, the data types are basically the same everywhere. And something that's relevant for us is like this concept of what's mutable and immutable, because these are probably things that sometimes vary with languages. Mostly, I think they remain the same, but yeah. So what that means is, so like every variable in Python holds an instance of an object. Now there are two types of objects, like mutable and immutable. So whenever an object is instantiated, we assign it some sort of an ID that, okay, to identify that object, and we give it a type that is defined at runtime, and we cannot really change that, like the type. And so that when we cannot change that, that's called immutable. And if its state can be changed, then it's a mutable object. Like say you have a string. So okay, I'll just show you the slides and that would be easier. So these are just the basic data types, but yes. Yeah, I mean, this is basically just, like random number generators are like a very important part of most of the scientific software that we'll be using. So this is the default one that's built in Python. What we actually end up using is numpy.random. But yeah, so I think I have planned to talk about data types first and then mutability. So let's go by the slides. So yes, strings. I mean, this is just like probably other languages. And so we have like every single character, which is considered an element or something, and len is the length operator. Strings can be indexed just like lists or tuples. So -2 over here means you go back like 0, and then back means you go front again. So D is 0 because in Python indexing starts from 0. That's, I mean, sometimes when I'm, say, working with Julia and indexing starts from 1, so I forget that and it's a mess. But yeah, so keep that in mind. And so yeah, A is -1, T is -2. So and again, the last, the ending part of any sort of a limit or range, the end is it's like exclusive from the right hand side. And as in, what I'm trying to say is, say if you have this range x comma y, so when we give a range, we mean this in set form. So it's like, yeah, we include x and we do not include y. Now, yeah, immutability. So basically, immutable objects cannot be changed. Like that's what I said before, but we can like sort of see it in an example now. So yeah, say you have the string x. So when you do x plus umbrella, you get a new string. Or the value of x itself is replaced. So say you give x is PQR. Excuse my handwriting. PQR, and then you give x is equal to PQ. Now we are not actually modifying the value of x, we are creating a new variable x. So we're basically erasing this variable from existence. So yeah, the same doesn't go for lists. So yeah, which is why you cannot actually assign like I'm sorry, a particular a value to a particular element or index. So like, yeah, you cannot say that this part of the object will become this, because you cannot change it. The entire object changes or nothing happens. So there's no item assignment once you've created the item. And I mean, this does happen for lists, though. We can just take up a list and say that, yeah, this index is this. I mean, that's something that we're all used to doing. Polymorphism. So yeah, it's like every operator or function can mean different things for different classes, different data types. So it's like, yeah, even like this, I'm just taking a very simple example to just like sort of explain the intuitive concept. These are all like data structure concepts, algorithms concepts that you should probably learn in details if you really want to master the language. I'm just sort of giving you taste of it. So the word polymorphism basically means that it has like a lot of forms or something, like that's the literal meaning. So like same function or same operator has like different signatures or different impacts or whatever in different types. When you're adding strings, they literally get concatenated, and when you're adding numerals or whatever, then they just the arithmetic operator happens. Similarly, like len means different things for different data types. Like for this or for a list, in a list, we aren't going to count the length of each element. Similarly, if we have a dictionary, length gets evaluated differently. So yeah, that's basically a intuitive way of saying what polymorphism is. Related things are class polymorphism. Like a similar thing happens with classes. And say in classes, if you have a particular, say you have a base class and you define the function, and okay, let me just, this is my base class, and I defined x, y, z, these three functions in A. Now I inherited a class B and I defined x again. So now when I call b dot x, the new x is used, which is basically like method overriding. And when I do b dot y, we get this y because we didn't sort of replace it. Like the most important data type we care about is lists, because that's useful for storing data and doing actual large operations. So array operations is actually a very deceptive title. I'm here to actually do linear algebra. So yeah, lists are just like, the main thing is that it's indexed and it's a collection. I mean, you can basically have like different forms of data types in one list, a string and a dictionary, or I don't know, a couple of different data types. But eventually we'll see that we end up sticking to numbers. I mean, that's the most common kind of list that we'll be dealing with. Yeah, I mean, addition operations and indexing, just like strings, works with lists. So over here, -1 again means from 0, you go back. So 1.23, which is the last from the right side, last element from the right side is -1. Now we'll look at list specific operations. So it's like append and pop are basically removing an element and adding a new element at the top of a list. These are operations that are defined specifically for these lists. Similarly, you can do sort in reverse. I mean, those are things that you can do even without the exclusive operation names. Like for reverse, you just basically do this. Most of you probably know this. If you don't, we'll find out. So for indexing and slicing, I mean, we remember L was just 3 or 4 elements, and I tried doing L with an index of 99. So yeah, I got an error. I can index it with, oh no, this is not indexing. So yeah, over in this case, X is actually a matrix. It's like both of these coupled together. And so basically the number of elements in this X itself are just 2. So it's like a 2 cross 2 matrix. And yeah, again, X00 means this element, like 0th list. And inside the 0th list, we're looking at the 0th element. Now, this colon basically means all the elements in that range. So say we give L colon, it means all the elements of that list. You can basically use it to create a copy of a list. Like say if you do this, so basically you get a copy of the list. And say you have a matrix. So say X is a matrix, and then you can use both of these different sides, like this side of it and this side of it, to if you want to slice the rows and columns differently. So again, you can use the colons. So indexing is something that we'll be using over and over. I think I shouldn't have brought this matrix thing right now. It just looks terrible in my handwriting. But yeah, we'll reach it. 1 second. So yes, again, as I said, that -1 would mean that you're going right from, this is -1, this is -2, this is -3. So when you're saying -3, or say the length of the list is n, so saying n minus n semicolon nothing basically means you're traversing the entire list again. And this is really nice. You can basically get like the syntax for putting these semicolons is that over here you put the starting, like the index of the starting element, and the index of the last element, and over here is the step size, that at what step size do you want the traversing to increase or decrease, -1, -2, whatever it is. So over here we gave 1, so we started from 2, and we gave nothing over here, which means we end here, and we gave a step size of 2, so we got even numbers. Now if we did L0 2, we would get odd numbers. So yes. Now, yeah, again, over here, we gave starting and ending, no values for that, which means it's going to take the whole list. And then we gave -1 as the step size. So it reverses the entire list. Now, list comprehension. Yes, that's probably one of like the important things in Python. I mean, say you had a list, and you wanted to create a list, or you wanted to do any sort of an operation on a list in a for loop, or basically, in a particular orderly fashion, that this is a particular operation that I want to repeat, which is basically what for loops are used for. So you could do this, or you could do this. So you basically create a list at the moment. Now what this does is it's way more time efficient. It takes up way less space. And so you have like these iterative statements that you basically transform into an expression or a formula. Now, we're just going to take an example. So say we have this thing M, it's basically like a table. That's what it'll look like actually. So you have OS and percentage of users and something. Now, if what we're doing over here is we're doing list comprehension. So think of it in terms of the for loop again. So we're doing the for loop, and we're taking so all of these like the element of this list M. This is one element. This is one element. This is one element. This is one element. So row is this element, and we're taking row 0, which means we're just taking the operating system and not the percentage. And then eventually we're saying 1. So we're skipping the first element. So we're skipping OS. So as we see, we get Linux, Windows, OS X. Now, again, we're doing a similar kind of a thing. We're doing the same list comprehension, but this time instead of just printing those values, we're adding an asterisk. This time, again, what we're saying is, so basically row 0 again means the operating system that we're taking. And this time we added a condition that the first element of row 0, 0, as in the OS name, this is 0, 0, this is row 0, and its 0th element or first element actually is not O. So basically, this is just a way of eliminating OSX. This is a very simple condition. And the idea that I want to say is that, yeah, you can actually make up a lot of complicated conditions and filtering with a lot of arrays in a relatively more efficient and neater way compared to for loops. You can do the same thing. Like I basically created an identity matrix here. Like this is an identity matrix. And yeah, so it's like first I run a loop over here, n is 3. I could take any value for n. So first I run a loop where I'm like, if I and j match, as in these are the indexes, right? So when I and j match, we get a 1. When they don't match, we get zeros everywhere else, which is an identity matrix. The core thing over here is that, yeah, we can do this whole thing over and over. We can nest it, just like nested if else statements and nested for loops. We're just doing the same thing. Again, like this is just a condition. So we're saying among the elements 1 to 23, make me a list of elements which are divisible by 2 and 3. So you get things that are multiples of 6. Now we've come to lambda function. So this is basically just an anonymous function that you're using. I mean, it actually behaves just like any other function. You could give it any number of arguments, but it's just one expression, and you don't actually use the def keyword and define something. And you can use it as, like, you know, say while you're returning a function, you can actually do return lambda some expression. So returning a function in a way, and it's basically sort of neat to write, and it's often useful in list comprehension or any sort of array operation where you want to quickly give an expression for something that you want to do to the array. Now, say in this example, so over here, what you're going to get basically is, this is again list comprehension. So in the range 10, which means 0 to 9, that's how Python indexing works. You get like, so you get like 10, 20 up to 90, basically what we got over here, the same thing. But over here, you just created a lambda function. So lambda I is basically saying that for I, evaluate I star 10, as in the input is I, and the return statement means I asterisk 10, and which means multiplying, obviously. And so, yeah, and then you give the list range. So you're basically multiplying this I for I in range thing with 10. And yeah, that's basically lambda function for you. This is like the simplest thing I could think of, but yeah, obviously you'd actually have way more complicated things that would actually be useful. Now, NumPy is basically like, this is like the last part of this webinar and probably the most important. NumPy is another open source library that basically deals with multidimensional arrays, which will be useful for, again, all sorts of scientific open source software. And this webinar is just meant to be like a quick overview of it. So it demonstrates how those arrays are represented and how you manipulate them and how you do things like broadcasting and slicing them. I mean, indexing and slicing for NumPy works almost similarly to lists in Python in general. So yeah, let's get started. So like some of the like basic things that are the properties of an array in NumPy. It's called an ND array or just an array. There's ndim, which basically means the number of axes or dimensions of the array. There's shape. Now, this is like a tuple of integers, which indicates the size of the array in each dimension. So it's like for a matrix with n rows or m columns, shape is n comma m. And n, oh, this is thick, yes, n comma m, and this ndim could be 2. Size is the total number of elements, so it's like n into m. not cross. That's a different thing altogether. So yeah, let's get started. So say, usually there are different ways of creating a NumPy array, but say we took the function np.arange. It's similar to the Python function range that we use in for loops. So you basically created an array with elements up to 16. And then we gave this thing reshape. So basically we want to reshape this whole thing into a 4 into 4 dimensional matrix, which is what we get. Now let's just have a look at some simple array operations. So we're basically multiplying, and the only thing to note over here is by default, unless we specify using say np.dot or some other operation, at is another way of signifying matrix multiplication. These are very different things. This and np.dot are the same thing. And this basically is just the Hadamard product or element-wise multiplication. So yeah, you're not actually, with a scalar, it's not even possible to do matrix multiplication, but you know what I mean. So these are the general properties that we talked about again. So here's the shape, and here's the dimension, and then in size. Again, this is basically what we wrote down over here to an n comma m and n cross n into m, which is exactly what we're getting here again. Now there are tons of ways to create an array. You can basically just give np.array parenthesis and insert a tuple. You'll get a NumPy array. You can use inbuilt things like np.zeros, create a matrix of zeros. There's something called np.empty, and then there's something called np.ones. So you create a matrix of ones. So there are a couple of ways you can create an array. In NumPy, you can generate values in a certain range using the arange thing. Again, it's now, although if you have floating point values, I wouldn't advise you to use that. You should be using np.lenspace because of the precision. This would be this. It would be difficult to split this into 10 parts as such, because it is not very feasible to predict that how many elements can you get because of the point precision thing. So yeah, we should just stick to using that in those cases. Then yeah, just like Python's random thing, we have a random number generator even in NumPy. Earlier it used to look different. The way to initialize it. Now this is the way. So we take np.random, and now this is probably the relevant part. This is basically for reproducibility. So let's say you're generating a random array and you want to generate that again later on. You want it to be random, but you want to be able to test out things that you did back then again. So then yeah, the number that you give to a random generator, that's relevant. And yeah, now I generated an array of size 3. There's something called CumSum. So that's basically the cumulative sum against any axis. So in this case, we only had one axis. This is the only axis, but say we had a 2-dimensional matrix, then it would be better to specify which axis is in this side or this side. We would need to specify that to get the results that we actually want. So in this case, what happens is we add this and this, and then this and this plus this. It's like a Fibonacci sequence. Then multidimensional arrays. So again, this is just a multidimensional matrices. Matrices are multidimensional that we created using lists, just that kind of a thing. So yep, the shape over here is 2, 2, 3. Let's just have a closer look at this. So basically we have this is one thing, and this is one thing. So these are the twos. Basically you have these two. Inside each of them, you have these two again. This is where the 2 and the second 2 comes from. And then inside you have 3 elements, which means 3. So yeah, it's basically like a 3-dimensional matrix. And yeah, I mean, you can actually try out print statements to, if sometimes all these parentheses get very confusing and you're like, okay, I don't know which is, I mean, which of these is like lies along the first axis, or as in for the main matrix C, what are its elements, what are C's elements, and then there are elements inside the arrays that C creates. So like if you want to split it along the first dimension, so we do print, and yeah, we get like this part is one thing, this part is one thing, which is by the first two. You split this again, you get a 2,3 thing matrix. So yep, element wise printing. So there's dot flat. You can use it on an array and get all the elements separated. I mean, it's basically flattening the array. You're removing the braces, the dimensions. You're just getting the elements. There's a similar function called dot ravel. I mean, a lot of times in NumPy or even in pandas, things that are relevant are like whether something, when something gets modified, whether you're getting a copy or whether you're modifying the original thing. So that's basically the difference between dot flat and dot ravel. I'm unsure about how to pronounce it. Transpose. Yes, I'm here to teach linear algebra. So NumPy also has a whole module called np.lineal. So yeah, you should have a look at that. This is like a very simple operation. You're just sort of, if you have this matrix, this rectangular thing, you're basically making it a different orientation rectangle. You're just giving it a 90-degree turn. I mean, that's what we did to C. Where's our C? Yes, this is our C, and we did this. Now it is 3, 2, 2. That's the shape. Then there's reshape. We already used that, but here's again another usage. So you can basically, I mean, you have a certain fixed number of elements and you can reshape them into any shape you want as long as the dimensions add up. I mean, if there are 12 elements and I want to give them the shape 5, 3, that won't work out so well. But I can shape them 12, 1. Now here comes stacking. So say you have these 2D matrices of zeros and ones, and there's, I mean, these are just like the simple examples of stacking. So I just want you to know that yeah, you can actually take up all these multidimensional matrices and do whatever with them till it makes some sort of sense to you, which is basically what happens in linear algebra. No, I mean, that's not the way to learn, but yes. So basically this is vertical stacking. So you took this thing and you put it here. So this is your V stack. Then there's horizontal stacking, which is like you took this and you put it here. You joined them horizontally and vertically. That's like the only difference. Now, this is the last part. And again, the most important, I'm saving it for the end. So I hope you have some attention span left. I mean, I find it difficult to focus for like really long. So just bear with me. So broadcasting, yes. So broadcasting basically lets you like use universal functions in NumPy, or I mean, NumPy is not the only place where broadcasting is used, but that's what we're talking about. It lets you deal with inputs that do not have the exact same shape, as in they can be aligned in some ways, but they don't have the actual exact same shape. So say you have something like 2, 3 and you have 2, 1. So now these are arrays that can be aligned, but if you have, I'm sorry. Yeah. If you have 5, 6 and 3, 4, you're not going to be able to align them or do any sort of meaningful thing with them. Like remember in linear algebra for matrix multiplication, we need them to be of this format, as in these should match. So similarly for like a lot of standard operations. You need some sort of a match with the shape to create the output. So the first rule of broadcasting is that if all the input arrays, if they do not have the same dimensions, you'll add a 1 to the smaller arrays. Say we have this one smaller array, so you fill it with 1s until they have like the same number of dimensions. Like you just basically, like 1 is just this filler thing. And another thing that you do is, so say this array over here had the size of 1 in this part, like this dimension, and so this will basically act like it has the size of the largest shape along that dimension, like this one. And so that we're basically stretching this 1 to 3, which is like we're broadcasting it. So essentially we need the last dimensions of 2. Say we have these 2, x and y and p and q. We want to like do some operation with them, and for broadcasting to work, we want y and q to be compatible. So when can they be compatible? When they're both equal, or if one of them is equal to 1. Those are the ways that they can be compatible. If that doesn't happen, you get a value error and the operation does not happen successfully. So we'll look at some examples. In this case, these are both one-dimensional arrays, so you're going to have no problem. You're going to get a one-dimensional array back. This time you have a one-dimensional array and a scalar. So as you see, the scalar basically acts like a one-dimensional array. So yeah, I mean, this basically, like this is 1, 0, and this is just a scalar, not even an array. So yeah, broadcasting works fine over here. So intuitively, as the scalar is being stretched to, this other array, one-dimensional array. I mean, that doesn't actually happen, don't think that. So actually what happens is broadcasting is way more efficient computationally, and it also helps us deal with some sorts of shape mismatch and stuff. I mean, there are cases where it is like not a good idea, but that's like something that we're not going to go into right now, because that's like sort of out of our scope. So it basically like provides us a means of vectorizing a lot of array operations. So eventually a lot of NumPy operations actually happen in C, again because of computational efficiency. And we in broadcasting, just like list comprehension, we try to like sort of make less copies of data and try to implement those algorithms more efficiently, so those same operations are done in a better way. But yeah, it's not always a good idea. So yeah, your use case is something that you should be worried about, but in general, it's a skill we want to learn. So now this is a case where the dimensions aren't exactly the same, but they're aligned along the leading dimension, as in the leading dimension. This is what should be aligned, 3 and 3. This is the rule I talked about. So these match, so broadcasting works fine. Again, this is, so yeah, the leading dimension is 1. So just look at this. It's like we basically get the same thing in both of these. I mean, it's not actually the same. It's only the same because they're ones. So this is not a good example for that. But yeah, the thing is, we care about matching the leading dimensions. So the array that has like a smaller dimension, a smaller value of the shape of the leading dimension, is the one that is intuitively thought of as it gets stretched into the size of the larger sized dimension. And this only happens either if the leading dimensions are equal or one of them is 1, else it doesn't happen. Here's an example of it failing. What happens is our leading dimensions are different. You cannot possibly stretch them out, bring them together. So it's like basically you have something like this and something like this stacked into separate matrices. So there's no way you're gonna, because this is 3 and this is 2, this thing. So there is no way you're going to be able to do operations on them or spread them out in a meaningful way. So yeah, this is again just repeating the same thing, that they're compatible when the leading dimensions are equal or one of them is 1. They don't actually need to have the exact same dimensions. And yeah, this is another example of them failing. So yeah, the leading dimensions are different, and we're going to try to make it work. So what we do is we basically take a transpose. So here is A. A is basically a 1. So we basically just transpose the whole thing like this. So we basically create this. So now it's like 1 is the leading dimension. So then it's like, even if the other one is 3, this is B dot shape. So yeah, now it works. Now indexing. So we have this is like the last example we'll be dealing with. So we have an array, a random array A, one-dimensional array filled with some values. Then we have another one, I, that we'll be using for indexing. So we can index, so when we say AI, it basically means we're taking the array I, and instead of the index, we're filling it up with A, say 1, over here A1, A2, and A3. Those are what the values of I are. So it's like 6, 6, 9, 8. Yep. Similarly, you can do that even for 2D matrices. I mean, the shape is going to be of the index itself, like J. So we're basically just going to write out J again. And then we will fill it up with these values for A. So A3, as in the third element of A. 1, 2, 3. So we get 8, just like that. So yep. Now when we try to do A, I, comma J, that doesn't really work. So this is what this is probably one of the most important things that you'll be dealing with if you end up like working in for contributing to PyMC. There'll be like a lot of shape matching problems. I mean, that's something that's like very relevant for any computational thing. Like you have all these matrices of data and large operations happening, and aligning their shapes meaningfully and deciding their leading dimensions, etc., is like a little tricky. So this is just like a very simple example of like shape mismatch, like in the next slide. So over here, what we basically have is the array is one dimensional, so you cannot basically give it two indexes. Giving it not two indexes, I mean, like saying evaluating Aij is not possible for a one-dimensional array, right? So you make the array two-dimensional. Now we have 4, 4, as in 1, 2, 3, 4, 1, 2, 3, 4. We have this thing. But again, we don't get it because broadcasting fails. See, again, this 4, nothing, as in just a one-dimensional array. And this is 2, 2. So we need broadcasting to work again. So we reshape I into the same shape. We could have done it into something else probably, but this is like the simpler thing to do. And now it works out all fine. So what you're doing is basically AI, J for the values of I and J there. So you basically need the shapes of I and J to match, because that is why this thing will resemble both of them. So yeah, that's it. So next thing that you should take a look at is like the NumPy user guide. Like a lot of the things in this tutorial are from like either the Python's official tutorial or NumPy's, and that's probably the best place to learn. And we really look forward to seeing you in the other webinars and a sprint that's eventually happening. I hope contributing to open source and this session itself was fun for you. Stay safe.